Imagine a universe where every single electron, whether in your body, in the stars, or deep within the most distant galaxies, is actually the same electron. This wild idea, known as the One-Electron Universe Hypothesis, was proposed by the legendary physicist John Archibald Wheeler and later discussed with his famous student, Richard Feynman. At first glance, this might sound like pure science fiction, but when examined closely, it reveals an astonishing perspective on the nature of particles, time, and reality itself. John Wheeler, known for his deep and often unconventional insights into the nature of the cosmos, once had a striking realization: what if all electrons in the universe are just different manifestations of the same single particle, moving back and forth through time? He proposed this idea to Richard Feynman in a phone call, explaining that an electron could move forward in time just as we usually perceive it, but what if, upon interacting with another particle, it could also move backward in time? When moving backward, it would appear to us as a positron, the antimatter counterpart of the electron. This suggested that electrons and positrons are, in a sense, the same entity seen from different perspectives in the timeline of the universe. To understand this, we need to examine a key principle in quantum mechanics: Feynman diagrams. These diagrams depict interactions between particles in space-time. According to Feynman, an electron moving backward in time is mathematically equivalent to a positron moving forward in time. Now, let's apply Wheeler's idea. An electron moves forward in time, interacting with other particles. When it encounters an annihilation event, where a particle meets its antiparticle, it appears to turn into a positron. This positron then moves backward in time, retracing its steps to an earlier moment in history. When it encounters another annihilation event, it once again flips direction, becoming an electron moving forward in time again. If this process were happening continuously, then every electron in the universe could, in principle, be the same electron, zigzagging through time countless times. While the One-Electron Universe Hypothesis is speculative, it does connect with some key observations: identical nature of electrons. All electrons in the universe are indistinguishable. They have exactly the same mass, charge, and properties. This idea could explain why they are literally the same entity. Matter-antimatter asymmetry: if positrons are just electrons moving backward in time, then why don't we see equal amounts of matter and antimatter in the universe? Some physicists speculate that asymmetries in the way the universe evolved might explain why we see far more electrons than positrons. Quantum mechanics and path integrals: Feynman's formulation of quantum mechanics uses a principle called the sum over histories, where a particle explores all possible paths through time and space before an outcome is determined. This aligns with the idea that an electron could be reusing its own past and future paths. While the idea is fascinating, there are reasons why it isn't widely accepted. Where are all the positrons? If every electron is also traveling backward in time as a positron, we should see much more antimatter than we do. Decoherence issues: quantum mechanics suggests that individual electrons can be entangled or take superpositions, but we do not see evidence that they all behave like one interconnected particle. Modern quantum field theory: more advanced formulations of particle physics, such as the Standard Model, describe electrons as excitations of an underlying quantum field rather than as individual entities moving through time. Although the hypothesis is not taken literally in modern physics, it played a crucial role in inspiring deeper thinking about quantum mechanics, antimatter, and time symmetry. Richard Feynman later developed the Feynman-Stueckelberg interpretation, which formalized the idea that positrons can be treated as electrons traveling backward in time. This insight has real-world applications in quantum electrodynamics, QED, one of the most successful theories in physics. Even if the One-Electron Universe Hypothesis turns out to be incorrect in a literal sense, it remains an astonishing example of how physics challenges our perception of reality. It teaches us that fundamental particles may not be as separate as they seem, and that time itself may be far more mysterious than we can currently comprehend. The next time you look at an electron in your computer screen, a lightning bolt, or a distant star, take a moment to wonder: is this the same electron that has been traveling through the cosmos since the dawn of time, weaving its way through past and future to shape the universe itself?